Dear learners, greetings from IIT Guwahati. We are in the course Fundamentals of Compressible Flow, Module 8. The title of this module is Measurement Diagnostics and Experimental Facilities for Compressible Flow. So, in this module we have already covered 4 lectures involving classical measurement techniques such as pressure, temperature and velocity. These are nothing but the localized type measurements. Then we moved on to discussions on advanced measurement diagnostics. It involves optical methods like Schleran apparatus, shadowgraph techniques and interferometer. Then we moved on to the classical wind tunnel facility, and that is a subsonic wind tunnel. And for this wind tunnel, what are the measurement techniques that are available? We discussed them with a perspective that the wind tunnel is very unique with respect to IIT Guwahati, because this is installed in the mechanical department, and all the measurement tools are also indigenous and they are developed, and all the experiments are performed in the wind tunnel laboratory. Then we discussed about high speed aerodynamic test facilities. So, in these test facilities we covered some of the important aspects, or maybe this was just a introductory remarks about high speed wind tunnels, high enthalpy tunnels, and what are the issues that when we travel at high speeds. And one of the important issue is that short test times and fast response acquisition systems. And we will now move to last lecture of the module, and of course, this is the last lecture of this course as well, and this lecture is about shock tube and impulsive compressing machines. So, before the starting of this course, we started about isentropic flow, followed by the one dimensional flow and involving shock waves, and based on this we have normal shock waves. Then we move to two dimensional waves, where we have oblique shocks and expansion waves. And all these things, if you want to think about that, is it possible to see a shock wave? There are and other thing is that, is it possible to create shock wave in the laboratory? The answer is yes, and for that we have a shock tube, which is a classical facility at IIT Guwahati, and we will discuss about its indigenous aspects, because this design was done in house and they were fabricated locally and they have been installed in the Department of Mechanical Engineering. Since most of the things are indigenous, we did lot of activities, that means starting from design of the shock tube and conventional theory that are available in the textbooks, that has been implemented here. Then once you install the facility, then we also have to do calibrations, and this is what the unique facility, and subsequently we will try to give some introduction that how a shock tube facility can be further modified to a shock tunnel. So, this is all about the lecture today, and towards the end of this lecture I will summarize what we have seen in the compressible flow and how the next generation or ongoing research on shock wave can be useful for the community. So, let me give the brief content that has been covered as a compressible flow theory. We have normal shock wave and we have oblique shock. So, the normal shock, when it becomes weak, it becomes oblique shock, and if it becomes further weak, it becomes expansion fan. and we also developed the many analytical theories to cater the background for mathematical background for normal shock, oblique shocks and expansion waves. Then also we moved to another applications that flow in compressible flow involving heat addition and heat rejections. So these particular things, when you say heat is added in a one dimensional duct, and if the initial condition of this flow is supersonic, when heat is added, obviously there is change in the density and also different flow conditions can be achieved in the downstream side. Similarly, when the flow is subsonic, other different condition is achieved. So, this is about heat additions. Then we, under these heat transfer things, we discussed about the Rayleigh curve that governs the direction of the consequence of heat addition and heat rejections for the compressible flow. Then we move to compressible flow with frictions. So, friction is nothing but adding length or extracting length from the duct. So, when you add length, that means that we add friction into it, and due to these frictions, and if there is a compressible flow inside the duct or tube, then obviously we are going to change the conditions are going to change in the downstreams. So, this is all about brief theory that we have developed so far. Now, at the end of the day, our first thing that we ask, does the shock wave really exist? If it exists, can you see it, and or can you create a shock wave in the laboratory? These are the few things that remains the question mark. So, and we need to answer that everything is possible, because as I mentioned, the shock wave is a very short duration phenomena, and this short duration, if it is catered in a such way with high speed acquisitions, so it is possible to record the data which involves the shock wave propagation. First aspect. Second aspect, it is also possible to create a one dimensional tool in the laboratory in which shock waves can be generated. Now, one such tube which is a very classical tube, we call this as a shock tube. So, it is nothing but a one dimensional duct. We can say it is a tube, length and diameter may vary, and it is a simply duct which may be closed or open at one end and closed at the other end. One end is closed, other end could be open or closed. Then it consists of two compartments, we call this as a driver and driven sections, and they are separated by a diaphragm. Now, when they are separated by a diaphragm, so we can say that we can have different gases at different pressures in the driver section and driven section. Namely, the two compartments are known as driver section or driven sections. So, they can be filled with gases which needs investigations. That means, if these gases are exposed to shock wave, what is going to happen? So, such a things we can do that. It is a device to produce high speed flows with high temperature and high density, and since it is a one dimensional tube, we can say there will be a normal shock which will be generated and it will propagate. Now, how this normal shock will be generated? Because the driver and driven section side, which are separated by a diaphragm, the diaphragm is instantly ruptured. So, as a result, due to the rupture of the diaphragm, a shock wave is generated. Now, once the shock wave is generated, it propagates to the driven sections. So, basically giving more details about driven sections, it is a low pressure region which contains driven gas, mostly air or any test gas, and in this section there are many measuring instruments, and here the measuring pressure instruments we call this as a pressure transducers, because these are dynamic phenomena, and these measurements can be done at a particular locations. Now, in the driver sections, it is a high pressure side, and the driver gas could be air, nitrogen, helium or any other choice, but the ideal choice is that driver gas with a low molecular weight than the driven gas. So, this is mainly because if the driver gas has low molecular weight than the driven gas, we can say, or we can prove in the theory that it will give higher shock Mach number. Higher shock Mach number means higher momentum to the flow. Then we have a diaphragm which separates driver and driven section, and this diaphragm could be a metallic one such as aluminum, or it could be a paper or mylar type. That means, we can have a multiple layers of paper or a mylar materials. So, this and just to sustain the pressure difference between driver and driven sides, and this is what the complete picture is all about. Just to show you three situations of a shock wave. One is case A, case B and case C. In the first case, that is the initial conditions. So, as I mentioned that in the initial conditions there are two tubes. One is driver, and this driver contains a gas, we call this as a driver gas. So, in this case it is a helium gas. Driven gas, driven section or driven section tube, it contains air or any test gas which has to be exposed to the shock waves. These two things are separated by a diaphragm. There is a intermediate partition between this. So, initially when you see this tube, these driver and driven gases are filled, and we say it is a case A, and here and we call this as a end wall from both sides. It is the beginning wall and it is the end wall, and this end wall has a lot of significance. We will show how it is important. So, when we start these things in a conventional way, the initial conditions of driver sections and driven sections are denoted as 1 and 4. That means, driven section is denoted as 1 and driver section as 4. And here I need to emphasize that these are the standard notations followed in almost all the books, and although we can give different numbers, but when we refer to any of the books, these conditions, standard conditions are always ensured. So, the condition 1 means it is the initial condition of driven gas. Condition 4 means it is the initial condition of the driver gas. Initial condition, I mean initial pressure, initial temperature, initial density, molecular weight of the gas, all these are the initial conditions. Now, what happens when you have kept this gas filled, what you do is that you ensure sufficient pressure in the driver section, so that the intermediate diaphragm ruptures. Now, when it ruptures, now you see in the beginning the colors are given, that initial colors are given. Now, when these and the initial colors also suggest the different conditions 1 and 4. Now, when this diaphragm ruptures, so this is a kind of instantaneous ruptures, means that you keep filling this driver gas, and depending on the thickness of the diaphragm or strength of the diaphragm, it will rupture at a particular instant. So, it is a instantaneous ruptures. Now, once it ruptures, what happens? A shock wave is generated, because it is a instantaneous ruptures. The aerodynamic phenomena says that if there is an instantaneous change, then such a things can be viewed as a shock wave. So, shock wave gets generated and it propagates into the driven sections. So, basically when you are filling these driver sections, you are initiating compression waves into these driver sections, and all these compression waves merge as a shock wave, and it becomes and that propagates into the driven sections. Now, you can see that the change in the color here. So, when the shock wave gets generated and it propagates into driven sections, it compresses the test gas. So, initial condition of the test gas, and another instant what we look these particular things as B. So, in a way that when the shock wave moves in the driven sections, it compresses the test gas. So, as you can see, the color gets changed. Color gets changed means those regions the shock wave has covered, those regions gets yellow, means it has the gas which was in the driven section gets exposed to the shock wave. thereby its pressure and temperature also shoots up. So, we call this initial wave shock as a primary shock, and this primary shock when it propagates to the driven sections. So, at one instant when the shock wave is standing at this location, it means that this portion of this gas has exposed to the shock wave and the other portion, other side of the shock wave has not been exposed. So, this is at one particular instance. So, this phenomena can be viewed at any other locations in the driven sections. Now, when you see this at this location, if you try to think about what is the conditions now. So, the conditions now becomes initially it was 1 and finally, initial case it was 1 and 4. So, here also 1 and 4 is still there. So, when I say 1 and 4 that means at that instant the wherever whatever the gas condition is, that shock wave that gas has not seen the shock wave. Whatever gas has been seen the shock wave then we can see change in the color. So, when a primary gas shock wave is generated, so it is for this primary shock wave changes the color. So, as a result its pressure and temperature shoots up. But what happens is that when you have a primary shock and this gas and also we have side by side we have driver gas which was helium, and if the driver gas and driven gas, there you can imagine that there is a partition, that particular partition we say is a contact surface. So, here you can see this particular things which just demarks this color as a contact surface. So, it means that condition 1 is still the shock wave is not exposed, condition 2 is the gas for which shock wave has been exposed, and condition 3 is the partition that separate the driver gas and driven gas. So, and we say is a contact surface. So, before this we have the these are the contact surface which is moving, and slowly if you think there is a this color change you can mark it, and when you say mark it, this color change essentially says that side by side the conditions of gas, driver gas and driven gas gets changed. Now, in a sense that when you have a primary shock gets generated and it propagates to the driven sections, side by side we can view that we will have expansion waves also gets generated, and these expansion waves gets into the driver sections, and when these waves goes, and of course, these waves goes in a slow manner. So, when the expansion wave goes and the conditions also is changes slowly. So, that is what the conditions 3 and 3 gets generated. So, slowly with conditions 3 and finally, when the expansion wave moves and entire things 3 and 4 finally merges, and so they become a common conditions 3 in the last figure. So, basically speaking, shock wave moves in the driven section, expansion wave moves to a driver sections, and when the primary shock moves, it is followed by a contact surface also moves. Now, what happens the next situation? Now, one point of time the shock wave will what will have, it will go and hit the end wall. Now, when it hits the end wall, it will try to reflect. Now, when it hits the end wall, entire things becomes the yellow things, that the blue color becomes yellow, that means entire slug of mass in the driven sections gets exposed to the incident shock, and finally, shock wave is reflected. Now, when it is reflected to a medium which is already exposed for the primary shocks. So, that means the conditions further changes, that yellow region now becomes red. So, that means it is in the higher pressure and temperatures, and followed by and finally, this reflected shock will come and at some and of course, when it is contact surface is also following the primary shock. Now, when the reflected shock comes and some point down the line the contact surface and it will reflected shock will meet the contact surface. So, basically speaking, when such a things happens, we can say that test flow is terminated. That is because whatever test gas was air, when the contact surface and reflected shock they meet each other, it means that the test gas gets diluted with the driver gas. So, it means that the test gas gets diluted. So, we say test time is over. So, that is the catch or time duration available to us to perform the experiments. Now, when this happens, we can say the reflected conditions now becomes 5. So, there are 5 conditions 1, 2, 3, then 4 and 5. So, 5 conditions refer to reflected shock, 1 condition refers to the initial condition, region 2 refers to the primary shock situations conditions. And this picture gives a more clarity whatever I have explained here, that if you represent in a standard diagram, we simply call this as a XT diagram. So, this we can see the position of the driver and driven sections at the starting point, that is a diaphragm, one is observes, incident shock moves because its velocity goes up, and when incident shock moves and it is followed by a contact surface, and regions are denoted as region 1, incident shock has this is the region 1, this is region 2 and this is region 3. So, region 2 and 3 is nothing but a partition that makes this contact surface. Now, what happens? Region 5 is the location when the primary shock gets hits the end wall and reflects. So, the primary shock hits the end wall at this particular instant and it reflects. Now, when it reflects and if you try to extend this line, then what we can see is that if you just try to expose this. So, this is the time the incident shock hits the end wall and this is the time the incident shock meets the reflected shock meets the contact surface. So, this time duration we can mark it as a test time, which means that when it meets these things, that means contact surface has arrived, and this and when the contact surface has arrived, it will dilute the test gas. So, if you want to perform any experiments with a given condition of test gas, so the test time will be terminated upon the arrival of the contact surface. That you can see, or we can superimpose on this kind of things diagram, that is XT diagram, and this can be evaluated. And moreover, this particular condition we call is a tailoring. That means, arrival of contact surface will terminate your experiments. So, just to give another summary, and if you look at this test duration, this test time is about 1 to 2 milliseconds. So, that means and when you have this 1 to 2 milliseconds, by this process we are going to generate a very high enthalpy flow in the through this simple device, and also we call this as a impulsive device to create short duration force and heat loads. Now, another kind of important aspects that can be imagined, or we can talk this, that when you think about a gas which is exposed to primary shock as well as refracted shock, and this particular gas slug of mass has exposed to a very high pressure and temperature, and that means that slug of mass is available with us, but for a very short time. So, if you talk about within this test time, whatever driven gas was there, if we can say that driven gas was available to us for 1 to 2 millisecond durations at very high pressure and temperatures, then we can say it is a momentary heat source. That means, that kind of enthalpy is available with us during this short test period. So, this is what we call as a high enthalpy flows. A more clear picture it is shown here, that with different colors. So, if you can see, the blue color talks about incident shock, red color talks about contact surface, this green color talks about the expansion fan, reflected expansion waves. And what we see is that we are going to say that your test time is terminated by this, by arrival of contact surface. Now, this test and subsequently also many classical important aspects that can form, if you keep on happening do the test beyond your test time is over, we can see that entire gas, first thing entire gas gets diluted, and mainly because not only the contact surface arrives, your expansion waves also comes and hits the contact surface, or reflected wave. Now, there will be interaction of reflected wave with shock wave, and all these things gives a very complicated features, gas dynamic features. And of course, you do not deal with those conditions when you perform the experiments. So, this is the characteristics feature is that in from the X T diagram we can say we have a momentary heat source which is available to us for about 1 to 2 millisecond durations, and this heat source has very high enthalpy. So, this is the summary that we can get out of this. This is also another picture that takes you can see this particular picture was drawn using standard tools of shock tube for a real time shock tube which has certain dimensions, and these dimensions you can say there are about 6 tubes, and all these dimensions and each tube 7 tubes, and each tube has a dimension of 1000 millimeter or 1 meter tube. And if you can see here that and if you can use this theory, you can see that for this kind of dimensions we can actually see that how your incidence is generated and how your contact surface travels. So, this particular plot is gives the test time calculations which is for this particular shock tube, and in this particular case this is about 1.1 milliseconds. This is about 1.1 milliseconds which was available to us, 1.2 milliseconds, and this you can see here we did some simulations for this kind of this size of tube, and you can see that the momentary reservoir hot momentary heat source that is at condition 5 is available with a very high temperature region, and this is available for this short duration test times. And side by side when you think about pressure jump across the shock wave, because we have seen that we have incident shock wave and we have reflected shock wave, and we have to see that we have to also quantify how much rise in the pressure which we have. So, this particular pressure shows that we have some pressure transducer which are located in the driven section that measures the pressure jump across the primary shock and reflected shock. So, there are two pressure transducer and each pressure transducer sees this rise in the pressure. So, you can see how a sharp rise in the pressure is felt by the gas. So, what we can see is here is that if you look at the first red color transducer, red color location, and this is the location of first transducer, and that means first transducer is location number 5, second transducer is location number 6. So, if you from this real time plot we can actually calculate how much time this gas has taken to travel from locations 5 to 6, and through this we know the distance, we know the time from this pressure plot. So, distance and time will give you the shock wave velocity, and this first peak talks about the primary shock pressure, and the second peak will give you the subsequent pressure after the reflected shock. However, if you take and if you look at our test time, the test window is closed because immediately after the reflected shock there is hardly any time. If you can see, one particular transducer has some steady region, and this steady region is about 1 milliseconds, and this beyond after that there is further rise in the pressure, that is mainly because entire slug of mass also gets added up, because the contact surface has arrived, the high pressure helium gas also has arrived. So, all these things merges up. So, we do not take any data beyond this time scale. So, this is the characteristics features. Now, I will talk about when you something that whatever facility we have in IIT Guwahati in house, I will talk about some design aspects. So, in the design aspect of the shock tube involves that since we have a shock tube and we can say it is a pressure vessel, because it handles the pressure at very high pressure, because we can say expect a pressure may about 25 bar, you can go up maybe more than that, but then you have to think about different type of thickness of materials. So, when you start with this shock tube, we can start with the initial pressure of 25 bar it must handle. And so, when you are handling this, and because since all the sides are typically closed, so you can say it is a pressure vessel. That means, a vessel containing gases at very high pressures, of course for a short time, but it is a very high pressures. Now, when we have such a gas at a very high pressures, obviously we have to think about some kind of design concepts, and we call this as a theory of thin wall, and where we can involve the concept of hoop stress. That means, whatever material we are going to choose for the shock tube, it must withstand that hoop stress, that is circumferential stress. And maybe we can do some kind of simulation study for hoop stress analysis for about 25 bar pressures. We can do a 2D analysis, steady state case, 3D case, and all these things we can do that. And by doing this, what the at end of the day what we are going to get is the stress components at different locations. So, the cross section components, this is lengthwise. So, what we can say is that if you take a stainless steel material, and this particular analysis also can be carried out with different materials, and typically stainless steel is a favorable material to withstand very high pressure. Then some analytical theory of shock tube, which I have already mentioned, that shock wave can be treated as a moving gas, because if you are looking at this shock wave, we are looking it and at the point of laboratory frame of reference. That means, it's, and since it is a, you can say it is a one dimensional duct, we can say it is a moving normal shock. Through this moving normal shock analysis, and also we have mentioned the regions 1, 2, 3, 4 and 5, and we can calculate the pressure ratio. So, you all know that what is their initial conditions, and after these initial conditions, and of course, we know that the shock Mach number, I mentioned that how we are going to calculate. We can find the first the distance delta x by putting the sensors at that locations. We can calculate time from the pressure transducers. So, distance by time will give you the shock velocity, and we know the speed of sound, because we know the conditions in the laboratory, we can get speed of sound, we can get a shock Mach number. Now, once we get the shock Mach number experimentally, all the analytical theory can be developed through moving shock analysis, and in fact, it is unsteady analysis. So, first thing is that if I say P 2 by P 1, that is pressure ratio across the primary shock. So, your initial condition was 1, pressure jump across the primary shock. So, it is a function of Mach number, and here I have put gamma 1 means 1 stands for condition 1. So, once you have primary shock pressure ratio, primary shock temperature ratio, we can also get primary shock density ratio. Now, similarly, another important working calculation, it is very important that we also need to calculate the conditions after the reflected shock. The reflected shock situations, we can say pressure jump across the reflected shock is P 5 by P 1, temperature ratios are T 5 by T 1, and here I have involved, and all these things are function of Mach number. And if you see P 2 by P 1, P 5 by P 1, they are function of shock Mach number. Gamma 1 means the driven section test gas, the specific heat ratio of the test gas. If it is air, its value is 1.4. Another important aspect what we can see is that ratio, that is P 4 by P 1, and this P 4 is nothing but the pressure in the driver section that ruptures the diaphragm, that is the rupture pressure P 4 by P 1. And if you look at here, it is a function of the gamma value in the driver gas, and also it is the function of gamma value in the driven gas. So, you have a gamma 4 and gamma 1. So, here the challenge lies here, that if you have from this equation, if you take this gamma 4 for a monoatomic gas, that means if you take a lower molecular weight gas and use it, then we can have higher pressure ratio. So, here we can and also speed of sound will be different, because gamma 1 condition for air and gamma 4 is for driver gas. So, these two condition is going to change. So, through this process we can say that the shock tube condition of generating Mach number can be controlled by choosing lower molecular weight driver gas first thing, and this why this we are doing, because if you take lower molecular weight gas, we will get the shock Mach number will be higher. So, and in fact, P 4 by P 1 is nothing but your rupture pressure, that is decided by the diaphragm strength of this diaphragm. Okay. So, this is all about the theory of these things. Now, I will just explain that what shock tube facility we have in the premises of Mechanical Department Engineering, IIT Guwahati. So, it is a 7-meter tube, driver and driven. We can say, you can see this particular picture, that driver section is equipped with a high pressure gas cylinder, and driven section we have manometer, manometer, we have vacuum pump, which normally is done make it vacuum, and we also have some pressure transducers. We also have data acquisition systems and all to take this all the data. And in fact, we also have pressure transducers which can be mounted at different locations 1, 2, 3, as I showed some of the signals which gives the rise in the pressure jump across the primary as well as refracted shock. And of course, it will also, and also we know the since we know the locations, so we know the distance between 1, 2 or 2, 3, whatever way you take, if you know the distance and the time, we can get it from the pressure transducer data. And these are the some photographs. As you can see, this particular cylinder is a helium cylinder, this is a nitrogen cylinder, and these are the different tubes and the entire facility. Another important aspect of this is that first thing is that when you say diaphragm ruptures, the very basic questions that we ask really whether it is a shock wave or some other wave or compression waves. Typically, when you say shock wave, it is a merger of compression waves. When the compression wave merge and it has to be shock wave. Now, if you look at this particular diaphragm, which is its initial shape. Now, ideally speaking, we can put this diaphragm, and as long as we keep filling it, it will rupture. Now, when you rupture, our main requirement that your rupture should be instantaneous. And if you just keep this diaphragm, that means if you want to have instantaneous ruptures, then you must create some kind of indentation on the diaphragm, that at this particular location which is weak, and that should rupture first, and when it ruptures, it should rupture instantly. So, that is what a V groove type design has been kept in the diaphragm itself. So, this V groove design, when you do that, at the center of the diaphragm, the crack should initiate in the beginning of this center, and it should rupture instantly. So, it is a V groove, and this V groove it has to be. So, if you look at this particular thing, initial diaphragm is this. Now, it is mounted in this fashion. There are 3-4 photographs which says that different rupture modes of these diaphragms, and when the rupture is possible, that even compression waves has generated and it has created sufficient pressure to rupture. But whether that compression waves has merged, all the compression waves has merged to form a shock wave or not. To address this, if you can see, if your rupture pattern of this diaphragm comes in this manner, then we can say it is a formation of shock wave. And all other cases, diaphragm, although diaphragm ruptures, but we can, by looking at this rupture, nature of the rupture, we can say it is just a compression wave that rupture the diaphragms. So, that means it is not at all a normal shock. So, these are the some kind of standard observations by which we can make that whether a shock wave has generated or not. And these are the some sample plots. I have already explained this, how the pressure jump happens in the primary shock as well as the reflected shock. Now, another important aspects that I have talked about the analytical theory of the shock wave, and where we talked about P 2 by P 1, P 5 by P 1, P 4 by P 1 as a function of Mach number. Now, for the next important aspect, we need to calibrate. So, we need to calibrate, I mean that we need to find out the shock wave Mach number experimentally. There is some theoretical plots that is possible, and from this theory, and you have to put, when it means theoretical data, if at all, that is if the shock wave, because P 2 by P 1 is a function of shock Mach number, and theoretical curve can be plotted as a continuous curve, and side by side we have to superimpose your experimental data from our observations. If they are close to each other, then we can say this the shock wave is, we can say that our shock tube is ready for experiments. Now, here also we have to put some kind of error bars, that how accurately you are achieving the theoretical or analytical values. So, this process we call this as a calibration of shock tube using the standard working formulae. Now, moving further, as I mentioned in my previous lecture, the shock tunnel is another high enthalpy facility, and this is nothing but it is an extended or extension of a shock tube. So, if you look at particular part in this particular figure, so there are the shock tunnel essentially consists of two parts. One is shock tube part, and this is tunnel part. So, by tunnel part I mean this whatever high pressure gas which is generated as a test gas in the shock tube, we want to expand this gas in a nozzle. Now, when you want to expand this gas, this another nozzle is attached to it, and this nozzle and come test section, when you do it, then we can get a desired Mach number. That means, we have already created a high slug of mass, a high density and temperature, and we are going to expand it further. When we expand it further, that means we are creating a very high velocity or high Mach number flow, and that passes into the test section. So, this is how the shock tunnel mode is operated if you want a very high Mach number flow. So, and such facilities we call as a high enthalpy facilities, and they can cater Reynolds number of 10 to the power 6, and you can also have Mach number between 6 to 8, 6 to 10, depending on the nature of the nozzle we have. And here also the test time what we are limiting is again within 1 milliseconds, that is decided by the test time available for the model, or this, let us say if you are putting a Mach 6 nozzle, the Mach number of 6 is available to us for 1 millisecond durations, and it has an enthalpy of about 5 megajoule per kg, and if this enthalpy if you can use it, then you can perform the required testing in the tunnel. So, this is another version of same shock tunnel, which consists a CD nozzle, test section, dump tank, and this particular plot talks about a pitot time history, in which a pitot probe is mounted in the test sections. As you can see, there is a sharp rise in these things, and this of course, if you see this particular pressure transducer, it is a sharp rise, but it is not a sharp rise, mainly because the what data we are getting from P 2 and P 5, it is within the shock tube, and here what data we are getting it in test section, it is in the test section. So, that means the gas has expanded. So, gas has expanded means it has, that is the reason there is a whatever rise was supposed to be there, it is not exactly sharp rise, but it is a ramp rise, and of course, it is a pitot pressure measurements, and these are nothing but your static pressure measurement. And finally, in reality, whether we see a shock wave or not, that things that we can do a kind of visualization study. Unless and until you see a shock wave, we cannot really whatever theory you have developed and whatever way you interpret, unless and until you see in the eye, you cannot visualize the shock wave. So, this is a classical experiment which is performed in a shock tunnel using a electric discharge based flow visualization techniques. So, this is a flow past blunt body. So, we have a blunt body, and a electric discharge based technique was introduced, in which there is a line electrode and there is a point electrodes, and there is a Mach 5.75 flow which is approaching on this model. Now, when we create a very high discharge among this point and line electrode, then we are basically discharging the gas through a glow. So, and at the same time when we are through this discharge, that glow, what we have that happens, we are going to capture in a high speed camera. So, you can say there is some kind of line or hazy line, of course, it is a hazy line, but we can see that this line clearly demarks the nature of a carved shock, which is typically characteristics of a blunt body. And from these things we can say that really the shock wave exists. But however, in advanced flow visualization study will give a very clear pictures when you take this flow visualization study sample by sample, microsecond or millisecond or gigasecond time scales. So, if you can do this sampling at a very faster rate, we can clearly improve this quality of visualization techniques. So, the shock wave is possible in nature, and we can also generate in the laboratory. And finally, in the end, I will just summarize that entire course we discussed about a compressible flow theory, and we talked so many things about the shock wave, but what the shock wave can do it for us. So, we can say that using a laboratory tool, we can generate the shock wave in the laboratory. So, the theme of shock wave research spreads in many multidisciplinary streams that involves science and engineering disciplines, mechanical, aerospace, civil, instrumentation, mathematics, physics, chemistry and biotechnology. So, although it is a shock wave, but it has a variety of applications. Normally, when you talk about shock waves, people think of aerodynamic communities. So, there are many aerodynamic researches involving aircrafts, missiles, space shuttles and so on. So, aerodynamic research is one and in fact, the next generation vehicles for traveling to the space also is driven by the shock wave. We can say ramjet engines, scramjet engines, all these concepts are next generation vehicle to travel for interplanetary missions. Then we can say discussed about the shock waves can be tools that you can have many measurement diagnostics we can generate on your own to for high speed flows. We can think about characterizing new or innovative thermal sensors. Other application in the manufacturing or material side could be shock assisted deformation and manufacturing. Normally, when you deal with materials exposed to high strain rate loading, then using a shock tube, it is one of the approach in which we can induce high strain rate loading on materials, and from there we can study the material characteristics and behavior. Now, moving towards per engine side, we can think about potential biofuels, which is or alternative fuels or next generation fuels, and the shock tube, since it is possible to create a instantaneous means time high temperature time, then we can say we can study the ignition delay of biofuels, because if such fuels are exposed to instantaneous rise in the temperature at that conditions, how they are going to behave. And also it leads to high temperature materials. There are many applications that involve shock waves in wood science and technology and tea and coffee industries. Typically, wood science and technology when means processing of bamboos or woods can be done through shock wave exposure. In a normal process, what you used to do, like when you treat these bamboos or any woods, and the normal treatment process and treatment process through the shock wave is quite different, because those temperatures and pressures are achieved in a very short durations. Now, if the woods gets exposed to such a shock wave assisted process duration, their behavior is going to be different. In fact, some people have studied that taste of coffees and tea industries, coffee leaves they are exposed to shock wave, the taste will also get improved. So, this is another area which we can think of, and the medical application of shock waves involves that for the next generation injections. So, instead of needle, one can think of replacing the needles with a just a jet that will come out and hit onto the body. And if treated properly, and there are some drastic consequences of waves, shock waves, we can say that tsunami is kind of nature that if the shock waves are not handled properly, they can create a disasters, and such disaster things can be addressed if the shock waves are handled properly in the laboratory. And there are other kind of application like impact testings. One kind of impact testing as like bulletproof jackets, bombs, and there are also civil structures when they take about wind loads, maybe a kind of cyclone, during cyclone what type of wind loads that gets exposed. So, all these things impact testings or civil structures or defense side, the application is possible. And many times we can say that all these things experiment we do require, because we need to make our computational modeling involving shock wave dynamics. And why we require computational modeling? Because since we say the shock waves, there is no standard theory available, although we do it for some of the classical cases, but in a complicated situations the standard theories are not available. So, all these experiments will create a benchmark for computational modeling of shock wave dynamics. And last part is like a philosophical aspects. I have nothing to tell about it, because every human beings is at one point or other is exposed to some kind of unprecedented phenomena which is we are not supposed to hear, but at the same time if happens, then what is the your psychological state of your mind. So, these are kind of some thoughts process that apart from engineering it can go also to other humanities studies. Okay. With this I conclude this lecture for today, and also I complete this entire module, and hope you would have enjoyed these lectures. And in my last lecture, this is not about this, we are going to demonstrate or show the practical utility of shock tube facility which is available in the laboratory. So, thank you for your attention. Have a nice times. Thank you, and I will close this session and as well as the module.